Good morning, everyone. Hope all are doing fine. I am Kiran and I work for Juniper Networks. I am a software data path architect there and been working on cloud native routing technologies. Along with me is my colleague Shailender. He is the technical lead in the team. Together we'll be talking about some of the work which we've done on quality of service for a virtual cell site router. And the use case which we'll be mainly focusing today is the 5G front haul. With that, I'd like to start my talk by showing the evolution of the RAN from a legacy non-virtualized site to Open RAN architecture. The evolution is mainly about the RAN disaggregation. So the legacy non-virtualized site consisted of the BBU or the baseband unit and the RRH or the remote radio head co-located at a single physical location. The RRH processes the incoming and outgoing radio signals, and the BBUs did digital signal processing of the uplink and downlink data traffic. The BBUs were connected to the core via backhaul transport network. Then some of the service providers evolved this topology and came up with what is called centralized RAN or the CRAN. So here, they moved the BBUs into a central location. So the central location, like a data center, provided advantages like centralized cooling, and improved power efficiency and easy management of the radio network. The BBUs connected to the RRH using front haul transport network. Note that these are just physical pooling of the servers and there was no cloud involved here. Next came the virtualized RAN or the VRAN. Here the functions of the BBU were virtualized and moved to the cloud. The cloud offered agility and scalability. But the interfaces of the BBUs and RRH were still proprietary, meaning the vendor interoperability was not possible. Then came the Open RAN, which made the interfaces open and standardized. BBUs and RRH were further disaggregated into what we call RU or the radio unit, the CU or the centralized unit, and the DU, which is called the distributed unit. The RU and CU were called the front haul, and all these CU, DU, and RU came in the form of a pod or a virtual machine. Some of the functions like DU and RU could be orchestrated in a cloud-native manner using any orchestrator like Kubernetes. There was a new network element called the RIC, which was introduced to provide intelligence to the RAN network. So service providers used RIC to onboard third-party X apps or R apps into the network. So now, let's take the case of the front haul. In case of a physical DU, there needed to be a physical cell site router to provide the transport network, but 5G had the option of virtualizing the DU, so there need not be any physical cell site router here. So instead, there can be a virtual cell site router, which can be run. It's a pure software router, which can be run on any x86 based Intel hardware, and also can be orchestrated in a cloud native manner. In addition, the VCSR can also host the VDU function. So this was about the RAN disaggregation. So now this We'll talk a little bit more about the virtual cell site router or VCSR. So this slide shows the capabilities and requirements of what a VCSR should have to cater to different use cases and solutions. Service providers use different technologies or deployment methodologies in 5G. They can be all the way from layer 2 to layer 3, or SR MPLS to SRv6, IPv4 to IPv6, BGP to ASICs. It varies all across. So the VCSR should cater to all these requirements. For the front haul, generally layer 2 or layer 3 is used, and for the mid haul and back haul, layer 3 is the choice. Segment routing is very popular here. For overlay services, people use VLANs using different layer 2 technologies like L2 VPN, VPLS, or VPWS. Now, if you talk about the latency requirements of 5G, so 5G offers very low latency compared to 4G. The latency, in fact, between RU and DU needs to be less than 150 microseconds. So it is very latency sensitive. So this is where we need to have a VCSR which should be able to produce very low latency, and care should be taken. Additional latency is not introduced here. So the end-to-end across all the components of the 5G needs to be less than 10 microseconds. 10 milliseconds. And there is also this control data and management traffic by the ORU and the DU. The VCSR should be able to assign appropriate priorities, to these kind of traffic. Now, if you zoom into a little bit about the high-level block diagram of VCSR, this is how it looks like. As I was mentioning earlier, VCSR is a pure software router which can run on any x86 server and can be orchestrated in a cloud-native way using Kubernetes. And this is very much suited for 5G use cases because 5G is also cloud-native. At a high level, the VCSR has a control plane and a forwarding plane. The control plane houses protocols for routing like BGP, ISIS, OSPF, and things like that. And the data plane or the forwarding plane is DPDK based, where the virtual router or vRouter runs. This provides very high throughputs, so that is the reason it is based out of DPDK. There is also this ODU, which comes in the form factor of a pod or container and is plumbed into the forwarding plane using a container networking interface, or what we call the CNI. The ODU exposes different interfaces towards the mid-haul, like data management and control. We call it the F1 interface. And the communication between ODU and the forwarding plane is generally, it can be, vhost user. For the front haul, for the RU side, ODU bypasses the forwarding plane and directly uses SRIOV to communicate with the RU through F2 interface. And for providing cloud-native functionality, there is a lot of Kubernetes machinery here. So there is a kubelet service which helps in spinning the pod. And Multus is here used to provide different CNIs like SRIOV CNI and CSR CNI. So this is the high-level block diagram. Now, a little bit more, we'll go to the QoS, and this is the architecture of QoS in 5G as defined in the spec. The 5G introduces this concept of QoS identifiers. So here, QoS is associated with individual flows. A flow is nothing but a data stream between the UE and the network. Each flow is associated with a QoS identifier, which identifies the parameters of the flow like jitter and latency and throughput. So 5G QoS has much more granularity and flexibility compared to 4G. Instead of having a single QoS value assigned to the entire radio bearer, 5G has a provision for having multiple flows with its own QoS requirements in the same radio bearer. So this helps the applications and services to receive tailored treatment based on their needs. Also, multiple QoS flows can be mapped to a single GTPU channel between the G node B and UPF, unlike the 4G. In terms of the mappings in the uplink direction, that is direction from UE, which is nothing but your mobile phones, UE to the network. The UE does the mapping of the QoS flows to the IP packets. And in the downlink direction, the UPF function running in the 5G core does this mapping. And the DU, which is running on G node B, translates these mappings to appropriate priorities, which is acted on by the VCSR. Now, there are two ways to implement QoS in VCSR. We have a way in hardware as well as the software. In the hardware, we can use NIC cards like E810 or X710 to implement QoS, and it is mainly suitable for bare metal servers, which has direct access to the hardware NICs. Here the hardware, does all the QoS functionality like, scheduling and queuing. So advantage of this method is that the hardware, because it's offloaded to the hardware, we get higher throughputs and performance. But the disadvantage is that it is not portable because it is dependent on the NIC. And it is mostly, NICs are fixed pipeline, so they are not tunable or customizable as per the needs. So the other way is to implement this QoS in software, and this is suited mainly for cloud environments which have VirtIO-based virtual NICs. Here, the queuing and scheduling of the QoS is done entirely in software. So advantage of this method is it is very much portable because it is hardware independent. And it can be tunable and customizable if there is any optimizations that needs to be done because it's just software. But the disadvantage is that it has a lower throughput compared to hardware because software is the one which does the processing, and sometimes entire CPU cores needs to be assigned for this functionality. So in the rest of the presentation, we'll talk mainly focus on the software-based QoS and how DPDK is used to implement this use case. And I'll request my colleague Shailender to talk you through those slides. Thank you.
Good morning, everyone. So with high-level architecture, we have a clarity now on how 5G high-level architecture works. So we will stick to the DPDK specific things. So this is a cost pipeline. It is well known. We have a classification, policing, and marking at the ingress level. So classification is basically association of incoming traffic with the specific traffic class or forwarding class. This classification is very important because if you cannot classify the incoming traffic into voice, video, different categories, you cannot act on them in the further cost blocks like shaping, scheduling. Categorization is like the primary start for the cost pipeline. For the policer, now once the classification is done, like I mentioned, it gives you a result as a forwarding class. And the classification is done on the DSCP bits. For V4, we have toss byte, and first 6 bits of the toss byte are the DSCP bits. Similarly, for V6, we use TC byte. They are called differential services. And we use code point to program most of the classification rules. We'll be referring to them as DSCP bits in the upcoming slides. So polyser takes input from the classifier. So classifier basically has given the forwarding class and the loss priority. Loss priority is mapped to the color. Loss priority high means a probability of dropping the packet in the cause is higher. Loss priority, we have 4, high, low, and medium high. These are mapped to actually 3 colors in the backend. So high means red, medium together with the yellow on the color, and the low means green. Once we go to the polyser just works on the colors. Now polyser, we have 2 types of polyser in DPDK implementation itself, SRTCM and TRTCM, single rate tricolor meter and 2 rate tricolor meter. For both, they work in color aware and color blind mode. Color blind mode means whatever classification has marked the color or the loss priority, the polyser will not look at it, it will not honor, it will just act on the configured rates and provide you the output color without considering the input color. In color aware mode, it does take the input from the classifier color and then work on it accordingly. So for example, the input color is green, so output color would only be yellow or red. If the input color is yellow, the color would only be yellow or red. If it's red, then it stays red. So that's for the polyser. Now, once we have the forwarding class and DSCP bits are associated with the forwarding class, we call that packets are marked in the pipeline. So next block in the pipeline is at the egress, that's a rewrite. Now, once the packets are marked by the classifier, you have some certain requirement or certain use cases where you want to override the values depending on where you are forwarding. In router, you have multiple interfaces. Packets are coming in from multiple input interfaces going out. And input priority or input classification is done for overall traffic with certain rules. And you want to send the packet out, but you want to change the priority, you can do that using a rewrite. So it will override the DSCP bits for the particular forwarding class. The next module is the shaper, scheduler. Scheduler has submodules like shaper and the congestion management. Scheduler is implemented in our pipeline as a separate block. So what scheduler does is we have a forwarding class, or once we have an output from the classifier and the polyser, which is a color or the loss priority. Scheduler input is mapped with that forwarding class. So forwarding class to the scheduling. In this particular example use case, we will be showcasing only the strict priority scheduling. There are multiple different scheduling algorithms, but for simplicity, for use case, we'll be talking about strict priority scheduling specifically. So forwarding classes will map to the queues in the scheduler, and that's will be the input to the scheduler. Now output from the scheduler, as part of scheduler definition, you can configure rate, congestion management parameters for different drop profile using different drop algorithm. In DPDK, we have WRED and the PI support for dropping the packets. We will use, for our use case, we will just showcase the WRED in our configuration in the backend to drop the packet. So this will help us achieve, because we are doing the strict priority scheduling, we have a chance where high priority queues can starve the lower priority queues because you have traffic coming in from multiple interfaces and your bandwidth is limited towards the egress. So in 5G use case specifically, we typically apply the COS or the scheduler towards the mid-haul interfaces. So multiple RU interfaces are aggregating the traffic, and traffic is going towards the core on the mid-haul interfaces, and that's where we apply the scheduling. So you would have an option to choose disable or enable scheduling per interface basis. This is the existing DPDK pipeline, which is supported from a really long time in DPDK. We have packet parser, packets coming in and the RX. We apply the classify polyser, and then the packets get load balanced to the different worker cores, and then eventually combined at the later module at the scheduler, and then TX out. This pipeline we are showcasing for VCSR because I talked about there are requirements to do selectively on some interfaces scheduling. It is processing intensive, so what this diagram is showcasing is also the use case where the pods are connected to the router. You have a physical interfaces. For example, in this particular diagram, we have a fabric WIF1 showcased here, which could be VF or a PF. In certain use cases, because ODU exists and some customer says we don't want to touch our code, we don't want to modify our application, it works on SRIOV, just use the SRIOV. So we use the VF, the interfaces towards which are in the DPDK will just act as a gateway. All traffic will be forwarded to the switch to those interfaces. But there are scenarios where the pod can act as has a capability to do the IO interfaces or MEMIF interfaces. So our CNI helps stitch those interfaces into the VCSR, and that can be the incoming interface for the router. So we apply, once we receive the packets at the forwarding core, we have received the packets, now we can apply the classifier, polyser or marking. These are our ingress blocks. Rewrite is shown on this, but it is typically after the routing decision is made and you have decided which egress interface you want to send the packet out on. Now, in this diagram, let's say your egress interface is interface 3, wave 3, which is a fabric interface, and on that interface you have not configured the scheduling, so it will act as a run to completion mode and packet will go out. Performance for this would be slightly better. For scheduler LCOs, if the egress interface that was selected from the routing decision has the scheduling enabled on it, it's a mid-haul interface and the packets want to be going towards the core. We are dedicating a separate LCore for this functionality, and this would do the scheduling, shaping, congestion management, all the blocks that we'll be talking in detail about, and then the packet will go out on a TX. So it's a hybrid of a run to completion or pipeline model, which fits the VCSR use case need. So what we will be showcasing now is how we are really leveraging the DPDK for different blocks, like what APIs we used from the DPDK for doing the classification, for polyser, for scheduling functions, and how it really looks like from the router point of view. You're doing a configuration in the router. So for the configuration context, we have taken a simple JSON format to represent any router can do this. Let me jump further into the classifiers. Now, classifiers are crucial, like I initially talked about also, because they provide the foundation block for managing and prioritizing the traffic. Without this prioritization, further blocks cannot act on them. We talked about the DSCP bits are used. So you notice here in this is, there are two types of classifier, a single field classifier and a multi-field classifier. In single field classifier, we have a loss priority and the code point mapping. So in the packet, the code point are the first 6 bits, like the DSCP bits. It's also referred to as a code point. So we match the packet, we assign the loss priority based on the configuration from the router, and this defines the forwarding class. Now we have a classification of a packet. We know it's a voice, video, based on the configuration, a user can select this. These are named as CLA1, you can name it as anything. That's the forwarding class definition for you. So in single field classifier, you expect the packets are already marked. They are coming in with the DSCP bit in a proper prioritization. Now there are cases where that is not the case. So what you want to do is you want to use a multi-field classifier, which can match packet on any 5-tuple rule, IP, ranges, masks, different combinations, and create a classifier for you. Eventually the output is the same, the loss priority and the code point combination is created, and we have a defined forwarding class now. Now loss priority, like I mentioned earlier, is also associated with the color. So the next module in the pipeline, which is a polyser, takes input as a color. This showcases the DPDK APIs. For a single field classifier, it's a straightforward match on the DSCP bit. But for the multi-field classifier, we use the ACLs. So it's well known, I don't go really into the details. So we define an ACL. Now for VCSR, it's a dynamic creation. So you can add and delete the ACL rules on the fly. That, like Kiran showcased, we are doing it over the gRPC as an example. ACL classify is for basically the packet matching. I'm not showcasing the deletion and other things for simplicity to keep the slide simple. This diagram explains the data plane view. Now, once you have programmed the rules down into the data plane, it's a table that showcases the code points and the loss priority and forwarding class mapping. So it basically also tells you which packet is having a what forwarding class association. In the packet, if, for example, the code point is programmed as 42, in the packet it will be hex A8 because first 6 bits are used. Next block is polisher. Classifier gave us an output of loss priority, and the data plane now has the programmed values and the mapping from the forwarding and the understanding of the forwarding class. Polisher, we have two types of polisher, SRTCM and TRTCM. Both work in colorblind and color-aware modes. And Polisher uses a token bucket algorithm in the backend to shape the traffic, rate limit the traffic. So we have, if you notice, we have two definitions. We are showcasing both the SRTCM and TRTCM definitions. There is a slight differentiation in the parameters, like tricolor meter, TRTCM uses two rates, peak rate and the burst rate. And eventually, based on the rate exceed or the configuration values, we decide what color of the packet is. And this is a well-defined standard. We have an RFC for this, and RFC recommends what kind of values you should use for the traffic classification. Applying this polisher in the packet path. Now, you have the polisher definition. How do you really stitch it in the packet path, right? So for that, we again use ACL. ACL can match based on the forwarding class and then associate that polisher with that forwarding class. So now we have two block stitched. We have the classifier and the packet can be polished together. Output of the polisher is color. Now based on the color, you can choose. If it's red, you want to drop the packets, you can drop the packets, or you want to take some other action, you can take that action. These are the APIs from the DPDK that we use. I am not showcasing here the RFC 4115, which is also implemented in the DPDK, and you have the APIs available. So we are basically defining a profile here in the configuration. You have a profile application to the meter flow, and then based on the color aware or color blind mode, you can call the API and it will give you an output of the color of the packet. And you can choose to drop or forward accordingly. This is the DPDK view, a data plane view of the programmed values. So we have an index. We have the name for the polisher, and we know it's associated with what loss priority, what color, what are the values configured. It's basically, so the last field is like PBS or EBS. In the single field classifier, you use the PBS, we are using the common field to display. Rewrite. Rewrite is applied on the egress after the routing decision, like I mentioned, on a router. So this can override the values of the classification that is done by the classifier or polisher. So this helps in deciding what you want to send to the next router. So there is, again, a classification or a standard for this, which defines per hop behavior, and accordingly you can choose the values. This showcases the DPDK view from the data plane, what it looks like. So you have an input, two inputs, forwarding class and the loss priority, and the output is rewritten DSCP bits. Next module is scheduler in the pipeline. So DPDK supports hierarchical scheduler. The representation are, you have a port on the top, port represent an interface. You have a subports, which represents a group of users. You have a pipe, which is basically used for a user or a specific subscriber. You have traffic classes, which represent different type of traffic. It's same as forwarding class. And then you have the queues on which you will be taking a queuing decisions, or based on, you can do the shaping and congestion management on those queues. So what we have done, like I mentioned, we will be using an example of strict priority scheduling here. In most of the VCSR use cases, it's 8-queue strict priority scheduling that most of the customers use. That's the most common use case. So what we are showcasing is how we customized or tweaked the existing hierarchical scheduler in DPDK for the strict priority 8-queue use case. So what we have done is we have one support, one port against one support, we have one pipe, and then we have 8 queues. So what we did is we just tweaked the profile settings, and this becomes like a 8 queue. There's no user awareness, no subscriber awareness. It's just 8 queues, and based on these 8 queues, you can, based on the loss priority or the classification of the packet, you can do the scheduling in the scheduler. These are the scheduler configurations. We have, this is just specifying, like, you can create a scheduling for voice with the different values. You can have a priority. Priority is basically in this particular use case was mapped to the queue specifically. So 8 queue, we have 8 priorities that can be mapped 1:1. You can configure the transmission rate, which is a criteria to shape the traffic. You have a drop profile, which helps in congestion management. Now, like I mentioned earlier in the strict priority scheduling, higher priority queues can starve the low priority queues. So that's where this transmission rate or shaping rate comes into the picture. You can configure the specific rate on the higher priority queue. It basically then you don't starve the low priority queue, and traffic can be tuned accordingly. Drop profile, again, we have multiple different algorithms for drop profile. For simplicity, we are just showcasing a red. You have min threshold, max threshold, and mark probability. If it's applied on a queue size, if queue size is below the min threshold, everything goes through. If it is higher than the max, everything is dropped. If it is between min and max, we drop the packet based on the drop probability. Denominator, if it is 10, the 1:10 of the packet are dropped. These are the APIs, existing APIs from the DPDK that we are using for this function. We have a scheduler port support and a pipe configurations. You configure those, and then you apply the profile. And then based on once the profiles are applied, you have the data path tweaked for the purpose. And then what we do is, how do you stitch the scheduler to the previous blocks, right? So you pass the color as an input. So we mark the packet in the RTM buff. So there's the API scheduler port packet write, which overrides the value. And internally, the scheduler code uses the color and the forwarding class as required. So then we enqueue the port, dequeue the port, and after the dequeue, the packet can be sent out on the physical NIC, TX. So this shows data plane mapping internally on how the priority queues are mapped to the forwarding class. What I did not show in the previous diagram was the map configuration. So you can associate a forwarding class to a scheduler, and scheduler defines the priority. For example, strict priority in a previous diagram, if you notice, was part of the configuration of scheduler definition. Sorry. So now all the scheduler definitions are mapped with forwarding classes. You can choose each forwarding class at what shaping rate you want to configure. You can choose to apply or not apply drop profile. Drop profiles are again applied per color basis. This is the drop profile definition. I talked about this earlier on what criteria we drop the packet, and the queue size is really important. This shows the packet path at runtime. So for this example, we had configured the scheduler port configuration to be at a 5 gig, and the incoming traffic was higher. So you notice here, the queue length is like free for the higher priority queues. So the packets are being pulled faster for those, and the lower priority queues are being starved. The queues are always full, packets are always dropping. So it's the starvation case I was talking about. Now, once you configure the shaping rate, you notice everything is equal. Still, the port is still oversubscribed, so we're still seeing drops. Average queue length on the higher priority, because each queue is oversubscribed. So that's why you're seeing those numbers. But low priority queues are not starved anymore. For future work now, we identified some limitations in the DPDK ACL library. For like our use cases, we see there are a lot of cases like people want to say match on port 100, port 500, port 600. It does not fit the mask capability that the ACL library supports, so we end up adding 3 rules. So we can implement the list maybe, and that helps us. We'll explore all this work and see if the routing use cases can extend these capabilities. So for the drop profile also, we have a very limited set. Even in fact in the red, we just do the max probability based drop. We have seen that we can do on a multiple level. The drops, you can create an interpolate graph, take multiple min, multiple max, and create a step graph, and that helps in the congestion management in a much better way. So we will see if we can extend the library for that. So runtime updates for router needs everything at runtime, right? So you can't have an init configuration and stick to it. So I think runtime updates APIs are missing. So we'll work with the community to extend it to update, to bring in the runtime updates. JCNR is an example of what I just showcased as a VCSR. we have everything implemented in the JCR and much more. And now we'll see if we can work with the community to have the better use case and bring those in. These are some references for classification, metering, and the cost framework that we talked about. So thank you. We can take questions if anyone has.
Thank you. A nice presentation. Thank you. First question. This is the scheduling for the traffic. So as far as I know, in 5G core, there's a component, PCRF or PCF, which does the traffic shaping for end users. And how does it map to your approach? Because if I remember, if I understand correctly, the CSR is the RAN part. So it's not the 5G packet core. It's on the edge of the network. So how do you implement the interaction with PCF? And the second question, you use Virtio user for interaction over F1 interface. So is it okay with you in terms of performance? Because if I remember correctly, it doesn't have zero copy option. So is it okay with you guys?
Yeah, so especially let me start with the Virtio first. So for the Virtio, what we see is the ODU, what we are doing is we are deploying at the RAN side, right? So you have multiple radio networks, multiple RU interface. So you have 8 different RU interface coming in, consuming the traffic. And then they are stitching it to the data plane or the router, right? VCSR. So what happens is the radio itself has a limited capacity. So on a particular cell site, so far all of our use cases, we have not seen the traffic going towards the mid-haul exceeding 25 gig, right? That too at an iMix traffic rate, not at a 64 byte packet size, right? And you have multiple such units. So we are talking about deploying like 20,000 units. So it's at a very small scale that is deployed at each. So this particular use case is talking about that. Being said that, we have the MEMF capability. You can use MEMF. You can use VF directly, SRIOV VF, where you stretch the traffic via the VF and that hits the router interface. And we act as a gateway for those pods. So you can do that. So you have multiple options. We have a transit router use cases. If you want to just work on the physical link, you can work on the physical link. So those options are available. Now, for the first question, because we are at the RU interfaces, there are multiple RU interfaces that are aggregating the traffic. So for this particular use case, you want to apply the scheduling or shaping towards the traffic that is going towards the mid-haul. What you're talking about, the PCRF use case, are towards the core.
So just adding, right? So in this slide, we are at the G node B level. What you are talking about is the 5G core, right? So the use case is a little different for us. So there is no PCF here. This is a DU functionality.
Oh, I understand. I mean, what's the, do you have an experience in doing integration with PCRS in terms of using that API for DPDK to implement the traffic scheduling in the 5G core?
So far, from the customer ask, it is mainly on the access side. Core side we have, but then we really haven't got any requirements for the PCF side of things. We have a VPC use case there, wherein we have a tunnel established from the G node B mid-haul, basically CU to the 5G core, right, and not really the QoS part of it. And you have that backup slide for the.
So do you see any limitations on changing things at dynamic, like the scheduling hierarchy, right? You cannot change at runtime, right? And RTACL rules you cannot insert at runtime, right? So how do you manage that?
We are able to manage that. We are not seeing, so for ACL rules, we curate a context and we switch the context together. And the rules stay within the context. So that way the ACLs are simple and it works. For the rate configuration, shaping rate works perfectly fine with the dynamic updates. The APIs are not there in the DPDK right now, but the shaping rate update, we don't see any issues. Especially in the diagram, in the architecture, if you notice, we are not doing it in a multi-threaded way. It's a single L core that handles the single NIC. So it really becomes seamless. So we dedicate the scheduler L core based on the NIC. One scheduler can have multiple NICs, but one NIC cannot be spread across the multiple scheduler L cores. Because the use case was very limited here, 25G was the max case, so this works very well.
Only the hierarchy cannot be changed. But
Hierarchy we are not changing because we have, like I mentioned, for a strict priority use case, we have fixed the 8 queues, and we never associate like the port or subports with the user or a subscriber. So it's based on the traffic class. So 8 queues are fixed, so scheduler hierarchy is fixed. We are not changing the hierarchy in this particular use case.
Okay. So ACL case, it's like a ping pong buffer, like you keep changing. Okay,
correct.
That's a good idea. Okay, thanks.
So we have done the changes for the dynamic updates, like what Shailender was saying. Maybe we'll need to upstream those changes. Right now it's in a fork.
Yeah, that would be great because this dynamic aspect is missing in DPDK. So this, if we can
Correct.
upstream, it will be good for community.
Sure, that's the reason we highlighted it here. Good.
Hello. So is this the QoS DPDK QoS implementation?
It's the hierarchical scheduler implementation.
Okay, DPDK.
Correct. Yes,
QoS.
correct.
In my experience, it has limitations more. It doesn't scale beyond 2K flows. Do you have experienced any limitations, and do you plan to improve that scaling? Because with scaling, if you can improve the scaling, it is very useful feature. But I think the implementation was done a long time ago by, I don't know who was the original developer, but after that nobody has touched it. But I think there's a lot of room to improve that scheduler for large scaling.
True.
Then it becomes very attractive.
Yeah, so in this particular use case, we are not really tying it to the flows. It's really tied to the packet match, and you just go to the queue. Queues are fixed, 8 in number, so we are not having a big hierarchy. So that way the scale numbers are okay, and we are able to do actually 25 gig with iMix traffic.
I mean, okay, so you're basically matching packets, not flows. And then...
and this packet goes to the queue, and pretty much queues are 8 queues, fixed in number. We are never changing the hierarchy of the scheduler.
Okay. So, okay. I mean,
25G, at least for VCSR use case, you never need more than 25G as per our experience so far. Yeah. And that too not with 64 byte packet size. We're talking about like iMix traffic. So the PPS is not really very high. So in that context.
So basically, I'm just trying to understand, you said you're doing packet based, right? That basically multiple flows goes to the same queue, right? Correct. In this case, how do you ensure that, consistency in the, end to end for a certain, because everything is flow based, right?
Sure.
People are all sending,
Sure.
HTTP, watching movies and stuff
Sure.
like that.
Sure.
So anyway, all right, thank you.
Yeah, my question is pretty much the same context. Right now we are using the 25 gig, but in the future, right, it will be like 100 gig and even more for PCI Gen 5 and Gen 6. So given that current latest all the vendor, right, CPU vendor, including AMD, we offering the high core count CPU, right? So given that, because right now we have more CPU to utilize, so you talked about some scaling kind of, the strategy while you're doing the QoS for CSR. So what is your approach, and think that is how we can utilize those many cores throughout your pipeline model? So
if I get the question correctly, you're asking about how do you scale this given that CPUs are more now, and then tomorrow if you want to support higher bandwidths, right, throughputs,
Correct.
How can you do that? So one type of scale which we've implemented here is we are tying one scheduler L core to one NIC. Okay, so if you have multiple NICs, let's say 4 or 5 NICs, right? This might not be the same VCSR use case, but for some other use case, because we have more CPUs, we can associate each CPU to one NIC, right? And the entire CPU is dedicated for the scheduling functionality. So even if that NIC is, let's say, 100 gig, it can do it because there is no packet processing done here. It is just queuing and scheduling, because packet processing which is more intensive, CPU intensive, right? The route lookup and next hop lookup, everything, that is actually done in the forwarding course. So this is one way, scalable way of extending this architecture. Okay.
Slightly different question. Working? Okay, yeah. Slightly different question. So you said this whole orchestration is happening as a pod. Is there a reason for using pod? I mean, is it?
Yeah. So for cloud native use cases, most of the customers have adopted Kubernetes, and they are using complete orchestration using Kubernetes. We have worked with vendors like Juniper Cloud Platform. We have basically many platforms, right? So it's like a generic, we are agnostic to the platform, but major cloud native use cases are coming with Kubernetes.
Yeah, so the purpose is just the containerization, or also being, like, this whole thing is being published as a service?
The reason is this workload, right? This workloads are containerized now. So 5G has, has the architecture of cloud native itself. Mm-hmm. So the ODU is a pod now, or container. Okay. Right, so the router should also be, in the same form, cloud native router.
Basically, the vendors, whoever we work with, they are looking for a unified orchestration platform. They don't want it to be a VM and then they bring in pod. How do you stitch it to VM?
Right. But my question was like, are we publishing this as a service, a Kubernetes service where you load balance also? Those features are.
So right now it is present as an infrastructure layer.
Okay.
But for this particular use case, mm-hmm. So there are other use cases where you're acting as a transit router, let's say. In that case, sure. In that case, it works.
Okay.
And this is maybe a kind of generic but very specific question. There's initiatives going around focusing on latency. Specifically RFCs regarding L4S, low latency, low loss, scalable throughput, where you typically have dual queues. So all applications using non-L4S aware protocols use classical queuing, and applications that are L4S aware use low latency queuing. And this kind of requires dual queuing or something else. What are your plans for L4S support?
It's in the pipeline. Right now, we have not done much work on that area. We are just using the cost scheduler from the DPDK for now.
Okay, so no plans to implement L4S as
not
scheduling in...
Not immediately.
No, okay, thanks.
All right, it looks like we're at the end of questions from the first presenter. Thanks, guys.
Thank you.